Okay, so we're on page 23, and so this is a continuation of the last lesson. And you are given an integral in either integral notation or limit notation. Fill in the missing notation. So what I'm going to do, guys, is I'm not even going to have you like take any notes unless you want to for like the first few minutes of the video, because I have to show you a very complicated formula, okay, which is this. And it's going to be nearly impossible to remember if you're just memorizing a bunch of meaningless symbols. So, I mean, of course, there's always going to be patterns that you could look for, but it'd be better if those patterns had meaning. So that's what I'm going to try to explain just real quick. So this is from like a previous year that I did this, and I just want to like read through this. So, okay. So first I asked in the past, represent the area of the first, second, third, and fourth rectangles shown in the picture below. So what I've got here is a picture of this function f of x. And there's like this finite interval, although I'm not sure what the right endpoint is. And the exact area under the curve would be like, perfect. But we can use rectangles to estimate it. So it looks like they're doing a right Riemann sum here. For each base, you go to the right endpoint and up to the graph for the height. So as a table, guys, and really the more you can understand this, the better. So pause the video to try to really understand the, what I say. So as a table, this is this graph right here that I'm showing. So the very left endpoint is 2. And then the first x value is just delta x to the right of 2. All right, so 2 plus delta x. And then the next x value is 2 plus 2 delta x to the right of where we started. Next x, 2 plus 3 delta x. And then finally 2 plus 4 delta x. And so for the corresponding heights, guys, for each of these heights, the way that you get them is by plugging the right endpoint into the function. So if we're doing a right Riemann sum, this difference would be our base 1, and our first height would be right there. Okay, because we're doing a right Riemann sum, so we'd skip the left endpoint. And then base 2, height 2, base 3, height 3, base 4, height 4. Okay, so this is where here we're expressing the areas of each of those rectangles. Because guys, in each of these cases, look at the base. The base is the difference. The difference is always 1 delta x. Okay, so for each of these areas, the base is 1 delta x. And then the heights, I'm just copying them like from the table. All right, so this gives us the area of each individual rectangle. And we want to add them together. Okay, that's what we're going to do in a moment. But first, so guys, let's imagine the kth rectangle. Okay, so we don't know, like it's not a specific, number rectangle, but it's the kth rectangle, whatever k may be. It could be anything. And so we could use the table or the picture, but if we just follow the pattern, guys, so the kth rectangle, this was the right endpoint of the first rectangle, of the second, of the third, of the fourth. So the right endpoint of the kth rectangle is going to be 2 plus k delta x. And then to get the height of that kth rectangle, you would plug that into the function for the height. And we've already established, guys, that each one of these bases is 1 delta x. So the base is still going to be for the kth rectangle 1 delta x. But, but that would be the height. Okay, now, so let's add up. So instead of just like, writing each of these and adding them up, those are the areas of the rectangles, we could use sigma notation, okay, which is what is done here. So this was like our formula for the kth rectangle. And we could do a summation from k equals 1 up to 4. So you'd have k equals 1, then k equals 2, then 3, then 4, and you'd be adding the areas up. Okay, sorry guys, I'm talking a lot. Okay, anyway, so that brings us to our big formula. Oh, yeah. Okay, let me go back here real quick, and then it brings us to our big formula. Guys, if I wanted the exact area, so the exact area under this curve, no over approximation, no under approximation, just the exact area, I would need infinitely many of these rectangles. And as I take infinitely many of these rectangles, delta x is getting very, very, very small because the length of the whole interval is not changing. That's a fixed finite interval, but the delta x is getting like extremely small. So anyway, back to here. If instead of k going from 1 to 4, what if I let k go from 1 to infinity, okay? But instead of saying infinity, we actually do it in two parts. K is going to go from 1. First, we say to n. Okay, first we say to n. N could be any number. But then we do the limit as n approaches infinity. All right, this is the notation that we're going to use in AP Calc. I have seen, beyond Calc 1 or the textbooks that have, instead of like this two-part notation, they just have an infinity up here. But this is what we're going to use. So now, okay, so let's write this. Okay, so the integral from a to b of f of x dx, that is the exact area under the curve, is equal to the limit as n approaches infinity of the sum from k equals 1 to n of n areas, And those areas have, excuse me, the height is going to be that, okay, except our endpoint is going to be like a, whatever the beginning of the interval is. So that's going to be the height, a general height, and that will be just a general base. So f of a plus k delta x. So that would be the height, and then times the base is delta x. And guys, since delta x is always the same for every term, you could actually pull the delta x out in front of the sum. That would be like factoring it out of parentheses. So that is done sometimes. Okay, now guys, we really got to try to understand this formula. So let me say a few more things. Sorry, I'm talking a lot, but if you're losing focus or this is just not working for you, you could pause the video and I can discuss this with you in class. But I'm going to keep going. So if you're with me, then stick with the video. So let me just establish a few more things, like notation wise. So let's do, all right, I'm going to do limit notation versus integral notation. Okay, just stick with me, guys. This is going to make the problems a piece of cake. So limit notation, integral notation. So let's think about the elements involved here. All right, so let's have, all right, so we're going to do base height. Okay, so we want 2 columns, or actually let's do 3 columns. 3 columns, 3 rows. Okay, in limit notation, we're going to have a concept of the base of a rectangle, and we're going to have the concept of a height of a rectangle, and then we're going to have the concept of an infinite sum. Okay, we need to have these 3 elements in order to express exact area under the curve. Okay, so in limit notation, the concept of our base is delta x. Okay, and this is in the limit notation, delta x. And by the way that you find delta x is by b minus a over n. So this is the length of the full interval from a to b cut into n pieces divided by n. Okay, so this is the base. Alrighty, now the height is going to be f of a plus k delta x. Okay, and okay, so you could think back to the table I did. You could see that's where we got that. In this case, our a, so a is whatever this starting endpoint is. Okay, so a plus k delta x, and then we'd have, yeah. Okay, so that's what the height is. Now, the infinite sum, the way that you do the infinite sum, the notation for that with a limit is the limit as n approaches infinity, and then I like to open up a parenthesis, although that's optional, and then you do the sum from k equals 1 to n. Okay, so I'm just kind of trying to break down the notation. Now, guys, when n approaches infinity, look at what happens to delta x. N is approaching infinity. This is getting very, very small because the top is a number and the bottom is getting enormous. So this is getting very small. So delta x is getting small. And in integral notation, we call that I can't say that word, infinitesimally small delta x. That's going to be in our integral notation. All right, this encompasses 2 concepts, change in x and n going to infinity. That's what this notation is supposed to capture. Okay, and then in integral notation, you're just going to use f of x for the height. Okay, and then in integral notation, this concept of an infinite sum is captured by this s. Infinite sum, so it looks like an S, and then from A to B. Okay, there's all that stuff. All right, guys, and now moving on to problems. So, okay, so we're going to do these problems together and go ahead of me, guys, at any point. Okay, you are given an integral in either integral notation or limit notation. Fill in the missing notation. Okay. Alrighty, so guys, the key to going back and forth between these 2 notations, the key is finding delta x and a plus k delta x. All right, so finding these 2 things, but forget about, we'll have to find the f eventually, but you always want to start off by finding those 2 things. Okay, so that's what we'll do. So for the first one, delta x is equal to the length of the entire interval. So from -2 to 8, that length is 10. Okay, and we're cutting it into n subintervals, so divided by n. And then the number of subintervals is going to go to infinity. Okay, and now we need a plus k delta x. So a plus k delta x is in this case equal to -2 plus 10k over n. Okay, really let that sink in. Okay, now guys, I'm gonna circle the elements here of notation as I, as I translate them. So, okay, so let me translate the n's first. All right, this is the infinite sum notation. So infinite sum with a limit as n approaches infinity, k equals 1 to n. Okay, and then, okay, so there's the infinite sum, and I'll put dx, I'm going to translate dx, and I'll put that at the end. Oh yeah, dx translates to delta x, which is 10 over n. All right, so let me open up some strong brackets. Oh yeah, I think I want to leave room. Okay, there's that. Okay, so let me put delta x in, which is dx. So that's 10 over n. Okay, and now, so right now with my notation, I have captured those parts. Okay, and now for the height, you look inside of here. Okay, f of x. Instead of f of x, I want f of a plus k delta x for my height. Whoops, f of -2 plus 10k over n. Okay, all right, so there's that, guys. So that's going one way. Let me just jump to one of these in case any of you just want to break off from the video. And, okay, but I'll go back and do more. Or actually, let me just do this one. So, all right, going the other way, we still want to find the first two elements, which are delta x and a plus k delta x. So I'll use this space over here. So delta x and then a plus k delta x. Okay, so and just like before, let me figure out the ends of my notation. All right, so whoopsie. Oh yeah, I guess that's fine. Yeah, that's fine. All right, so if I circle the ends here, okay, so this part, that infinite sum is going to translate into an elongated S symbol. This is delta x. Okay, so this is going to translate into dx. And I can see it right there, what delta x is. So 5 over n. That's going to help us find a. So, so if that's delta x, then a plus k delta x is 1 plus 5k over n. Okay, so if you see those elements, then we're ready. Okay, so let me fill in what I've got so far, what I've circled. So the integral from a is 1, and then just add to it the length of the interval, which is 5. So 1 to 6. Let me leave a blank. dx. Okay, so let me cross those out. All right, so I've included those elements in my notation, and now I just need to represent the height, which is just, in integral notation, the height is just the function, f of whatever variable you're dealing with, so f of x. So guys, what you have left over here to represent, let me make those parentheses bigger. Instead of inside the parentheses having a plus k delta x, we would just have an x. So this is f of x. All right, guys. I hope that was helpful. This is really hard every year for people, so I just want to give it my all, and we could talk about it in class.